Good afternoon. So, yeah, that creation of Axon Framework, when does one create a framework? I never intended to be the creator of a framework, and whatever I created at the time, 9 years ago, was not a framework, but other people decided to use it as such. It was an experiment that I was doing to get an understanding of CQRS and event sourcing myself in a time where you could not Google for CQRS because nobody ever used the term online yet. And Google would happily serve you information about cars because it would assume that the Q was a typo. But that was 9 years ago. Fortunately, we've moved way beyond the experimental stages, and it's now being used in production quite a bit. And a lot of our users, they take this naive approach to using Axon, and we'll get to that a bit later, and they get in trouble. It does not perform, and so in this talk, I want to talk about these performance aspects. So in a CQRS and event sourcing system, what are some building blocks that you can use to tune the performance to make it as fast as you need it to be? But before I founded Axonic and before I did this research project on CQRS and event sourcing, and this is a bit of a confession, right? I really made some horrible software in those days. It was terrible. And I feel very sorry for the people, if any, if it's still running somewhere, for the people that have to maintain that. But anyway, I moved on, got other stuff to do, so that trouble is on somebody else now. And the most dominant architectural style in those days, and that's what I used as well, was the layered architecture. I'm pretty sure you're familiar with this architectural style. And so you get UI logic in your user interface layer. You have your business logic in your services layer, or application logic, depending on the relationship between the domain model and the service layer, and the data access layer, that would be your infrastructure-related stuff, right? Database or some repositories and stuff would live there. And if you have a look at this domain model, generally you have this typically relational model, right? Everything is somehow connected to something else that is then connected to something, and in the end, it's all one big connected component or data model. And then we map these services onto them. And if you take an agile project approach and you have this greenfield situation, I'm pretty sure you've had this feeling that everything is easy and you understand everything, right? And we build this service, and this service conceptually matches really nicely with one of the entities in your relational model. And so there's the second service. But there is this time after a while where there's this service that wants to know about everything. Right? And that's where trouble starts. Everything becomes connected to everything, and you end up with something we'll see later. Oh, here we go, a normal SQL query. Now, I've been using a SQL query in this slide for a long time, until there was this meetup where I used the slide, and somebody said, well, your query was bad. I've got a worse one. And that was this one. He said, you have to promise me that the audience cannot read the SQL query. And that was a couple of years ago, and most projectors on meetups, they were not that high resolution. So you had 2 or 3 pixels per character, and that makes it pretty much unreadable. And then suddenly I was doing a talk, and I was using this query on a high definition projector, I guess one like this. You can actually make out every character. And I thought, oops, I broke my promise. So I started reading the query, and about halfway the first line I decided it was still unreadable. So I guess I'm safe. But this is pretty normal. I'll give you a small summary just in case you can't read it in the back. This query contains 22 joins and 6 subqueries. Let's do a little quiz. Who thinks the performance of this query is awesome? Yeah. Define awesome, all right? Yeah. It's awesomely slow, and it will take ages to provide you, unless all the tables are empty. In that case, it's pretty fast. more of that later. So what do we do in this case when, well, performance is nowhere to be found? Well, there's some really cool stuff that we can do. We can add all technologies that internet provides. We can add caches. We can add caches all over, right? There's different layers where we can use caches. We can use, well, we probably need some session replication, right? If we scale out, we don't want to bother about the user session. So let's make that easy for ourselves as well. And the best thing we can do to improve performance is worker pools, more threads. Okay, I'm being sarcastic, just to be entirely sure, right? Unfortunately, a lot of people still believe that if you have a thread pool and it's not fast enough, just give it more threads, and it will go faster. Right? I'll just say it one more time. That is not the case. So basically, the software looks a bit like this, right? It has all these characteristics of anything that moves fast. And let's do the same quiz again. Who thinks this car performs really well? It will probably, maybe, get you to the grocery store, and that's about it. It will not take corners any faster than any other car. And I'm also pretty sure that the spoiler will break off if you go anywhere at speed. Now I like illustrations. I like pictures to express a certain emotion I have when I do a code review. And I've done a lot of code reviews, and I've seen this a lot, and that's very interesting. But this is something I also see. This is a picture of a design pattern that you might know as the big ball of mud. And the problem with the big ball of mud is that, well, there's no internal structure anymore. It's all lost. And there's another thing about it. It is not made of mud. And in this case, there's the architect proudly sitting on top of his creation, right? So do not criticize his big ball of mud. So here's a bit of ancient wisdom. So I'm Dutch, and the Dutch like to put wisdom on tiles, right? So we have these Delft blue tiles, and especially the grandmas in the Netherlands, they have these all around with, well, not with this one, I guess, but frameworks aren't pixie dust. If you have this big ball of mud or crap or whatever it actually is, there's no point in throwing frameworks at it and make it faster, right? That does not work. And this was the basis of my research 9 years ago. And I came across this concept of what is now called CQRS, Command Query Responsibility Segregation. Right. It's a pretty tough word, especially after a few vodkas. And the thing about CQRS is that we can now split an application into different components with different responsibilities. And one part is responsible for handling commands, and the other part, or parts, are responsible for handling queries. And that allows us to create domain models that are focused at that specific task. Right. So on one side, we'll have a command model that is focused on how do we process incoming instructions to change the application state, versus the projections on the other side, or on that side, where they are optimized to provide information to whoever needs a certain information from our system. Right? And the thing that it allows us to do, we use events to synchronize between the two. Right? And the thing that allows us to do is optimize each part of the model for the specific non-functional requirements that we have. Right? And since this is a talk about performance, we're going to focus on performance as one of the non-functional requirements. So a model that requires, or that needs to handle 1 million transactions a second with a latency of less than 10 milliseconds for each transaction, you will spend a different amount of attention than to a component that will only handle 20 requests per second and has an acceptable latency of about 100 milliseconds. Right? There's probably different people, different amount of attention you put into it. And there's this other thing about CQRS. It's very often combined with event sourcing. And that is because the events that are typically emitted by this command model every time a change happens, they are valuable information. Not valuable just in the moment they were raised, but valuable for years, sometimes decades. So making sure that you have a reliable trail of events, that is the principle of event sourcing. That is what event sourcing will give you. So if we look at how that works, is imagine you have two services, right? An order service and some service that does some smart stuff with whatever happens in there in our system. And each service would have its own data store, right? Where it can persist its own data. And they would have their own models, right? Either data models or domain models or whatever kind of model you would have. And probably that order service emits events as it's doing stuff with orders, right? And this analytics component can use these orders to calculate how long does it take for people to complete their order, or is there a specific behavior we can find so we can trick them into buying more than they actually want to. In the end, in retail, that's what it's all about, right? Now this is not event sourcing, right? This is just an event-driven architecture, right? You're just getting events from A to B, and B uses the events that A emits. Now what's missing to make it event sourcing is that the order service itself should consume these events and use them as its own source of truth. So there has to be this loopback, right? That means the data store of the order service should not contain current state. It should contain this history of all the events that it published, right? And in that case, the order service would use these events to make future decisions or make decisions based on any decisions that it made in the past, right? And this is what makes the audit trail reliable, or the event store a reliable audit trail. So the event store is the place where you put these events for later retrieval, right? We're going to dive into that a bit later on how that works and what it is, what's performance related about it. Now Axon, as well as some other frameworks, they want to help you make event sourcing easy, right? And it's just as easy as, put some annotations on a class, put some annotations on a method, and the framework does the rest. That's easy, right? So if you put the right annotations, that's the hard part of doing it. You have to put the right annotation on the right method. But Axon will make sure that your classes are event sourced. They're probably built up based on their past events. Any new events that you emit, they're automatically stored in whatever you have as an event store. Now, in the other service, you would probably want to read those events and do something with them. So again, you put some annotation. In this case, it's just a Spring annotation. And some annotations to make sure that the correct methods are triggered based on events. Framework does the rest, right? There's nothing to it. And these two classes, well, except for maybe the event classes themselves, they're basically everything you would need, right? If you have a Spring Boot application, you can just create these two classes as well as your events, and you'll have a component that can actually work, right? So that's easy, right? That's the magic pixie dust we put on, and then it performs. Well, in reality, reality is not development, right? Reality is not the test environment. Reality is in production, where numbers are always different, and they're not just different, they're worse, right? Things just typically do not perform as well in production as they do on your development machine. Because very often your development machine has a few thousand events in this event store. Production probably has a few million events, or maybe a couple of billion even, right? So things are just different there. And we've had some complaints like, hey, Axon does not perform. Like, ooh, that's a problem, because we do benchmarking and we do believe it does. So what's going on? Yeah, we just created these two classes and we ran it in production, and after a while it stopped. Yeah, that's because numbers are different. So let's look at some of the problems that they typically face. First problem is storing data becomes more expensive as there is more data in the event store. That means over time, This is an actual graph of the measurements, and just to assure readability, I've overlaid it with this line. So I'm not faking any lines, right? This is the real numbers, and this is the overlay, right? No tricking. And as you can see, well, storage, the write throughput is going down as this storage increases, right? And pretty dramatically as well. Now, on the far left side, that's probably where you run it in your development and test environments. It performs great, right? The right is probably where you end up in production. It's horrible. But the reason it does not perform very nicely is generally because of one of our friends, the B-tree index, and generally, I would say, the way most relational databases work. These databases are designed to be able to access any data in a table with roughly the same amount of effort, right? But an event store has a very typical access pattern, and relational databases weren't designed. It's not their fault, right? They're not bad. It's just that they were not designed for this specific task. In fact, we found out no SQL database really out there was designed for that task yet. So if we look at an event store, what does an event store need to do? Well, the most obvious one is append events, right? An event store is a typical append-only data store. There's no updates, there's no deletes. And when appending data, it needs to be able to validate some form of sequence. So in general, when two events generated by the same aggregate. An aggregate is a consistency boundary as defined in domain-driven design. It's a consistency boundary where changes are essentially atomic, right? So you cannot have concurrency there, at least conceptually. So the event store would preferably validate the sequence to make sure that there's no append operations that are conflicting at any time. Another operation that it needs to do is to read the aggregates events. So read the events that were generated before by a specific aggregate. And there's a very typical pattern that the most recent events are most likely to be read. Right? The older events become, the less likely they are read. And we'll see why in a couple of minutes. And the last one is a full sequential read. That's where an event handler would start reading from some point and just wants to read events going forward, right? Now, these are very typical event patterns that allow us to optimize our event store in certain ways. And one is partitioning. Now, this works in a relational database, and this is also what we've done in Axon Server, where we have this data store as well. And essentially, file system proves to be pretty good in appending, right? You can open a file and append data to it. That's pretty straightforward. So we create partitions. We create these, we call them segments in our product. But so we create these segments of the event stream, and every segment is stored in a file. And the most recent segment is kept in memory. The file itself is obviously on disk. The data is persistent on disk. But we have this index, and the index is kept in memory very aggressively. Right? Because we know we are writing to that index, and we are reading a lot from it. Now, as the number of events grows, we just add a new partition. And then what we do is we store the index of the previous partition, because now it's not being written to anymore. We write that to disk. Right. We have a stable tree, we can optimize it, store it on disk. We use a Bloom filter to make sure we don't need to load indices in which the data that we are looking for is not there anyway. And as time progresses, we add more files, that one gets added to disk, and now we can decide to remove the oldest one. Now in practice, there's going to be more segments in memory than just 2, but we can remove the oldest one from memory, because the likelihood of us needing to read that data is a lot lower. So we can dedicate our memory to that part that is important. And then we ran some benchmarks. And obviously, well, I wouldn't be standing here showing the benchmarks if it weren't like this, obviously. And what you can see is that line is pretty horizontal. In fact, it goes up a bit. So if there's more data in the store, it gets excited and it goes faster. Actually, in one of the test runs we had, you saw the line go up dramatically and then go down again. And we were like, what happened? And we checked. So this was running on Google infrastructure. And we checked with them, and apparently there was a bug in some Google service, and they gave us more IOPS than we should have been given. So that gave us some trust in the performance. We can, if we buy bigger disk, we get more IOPS, and then therefore we can improve performance as well. But you can see it's very stable. It doesn't matter how much data we have in the store, it remains stable. Now you can do similar things with a relational database, by the way. It's not, you don't need specialized services per definition to do that, but it just manages it automatically for you. So that covers problem one, right? We can now insert the same amount of data per second regardless of the amount of data that we have already stored. Let's look at some other problems. Now, the effort to read an aggregate, you can imagine that as an aggregate produces events, you need to load more events to get the state of that aggregate, right? To recalculate the amount in your bank account just based on all the transactions that you've done in the past, I'm pretty sure that's not a fun job to do anymore, right? If you just open an account, you probably can, because it's one page and you can get it done. But if you've been running it for a few years, that's pretty annoying. Now, a computer can do the counting much faster, but still it takes more and more time. So essentially, the loading time is a linear, right? It's a linear problem. So as you have more events, if you get twice the amount of events, it will take you twice the amount to initialize the current state, to calculate the current state of an aggregate. So one solution is to cache, right? Caching is easy. We've seen it before. It's the pixie dust you put on any application to make it perform. Now, the problem with caching is that we expect this. We expect that if we use a cache, that loading becomes a order of magnitude 1 operation, right? Because it's right there in the cache. We just pick it. Unfortunately, in reality, caches don't work the way we want them to work. They make good things perform well. If you design well, it will perform well. If you design poorly, it will perform poorly. And this is the actual results that you would get when using caching. And in many cases, it's worse than not caching at all. So why is that? That is because many of our users are using this in a distributed environment. So just imagine there's a client and there's 2 servers that can handle these requests. A typical load balancing strategy is round robin, right? Round robin is not your friend in this case. So let's imagine first request goes to the server on the left. That's great. It will do its computations. There's a new creation. It creates an aggregate with a certain state, and it emits an event, and that event could be given sequence 0, right? I like starting counting at 0. Now let's say the second request goes to the other machine. Well, that will work. That's not a problem. It will load the events, 1 event, so that's pretty fast. It calculates the new state, which is B, has a sequence 1, which it appends then to the event store. Now our event store knows of sequence 0. Fantastic. Now we get another request, and it goes to the machine on the left. Great, we've got caching. Loading takes no time, right? So we're fast. We're very fast at concluding that we need to insert sequence 1, but that's a conflict. Crap, transaction failed. We need to invalidate the cache and retry. Now, for making progress in this talk, I send this request straight to the component on the left again. And now it reinitializes, calculates state 2, changes the sequence to 2. And guess what? The next request goes to that machine again, and we start all over. So instead of the cache giving us advantage, it's giving us a disadvantage because it's forcing us to do 2 round trips. Fortunately, the solution is very simple. It's consistent hashing. So typically, the commands sent by components in a CQRS-based application, they carry the identifier of the aggregate on which the command needs to be executed. You can use consistent hashing to make sure that these requests are routed consistently to the same machine if they carry the same identifier. And that is very practical, because that ensures that you will hit a node that is most likely to have that information in its cache. Right? And then this is the performance graph that you would get. So it will basically be 1, but every now and then you will just have a spike, a big latency spike. Now, if you're in a high-performance environment, these spikes are your enemy, right? You can have great performance, but and this is usually when it matters most, like you're adding nodes because you're getting more load, you've got more workload, you're adding node, and then suddenly there's all these latency spikes, making a bad problem worse, right? You're getting more load, and now you're adding latency. And these are because of cache invalidation, right? Every now and then, cache entries are either invalidated, or even with consistent routing, when you change the infrastructure and the number of nodes, there's some rerouting to be done, right? In that case, you'll hit a node. So what can we do to make sure that these spikes go down? There's a concept of snapshotting. So snapshotting is a process where, given an event stream, just imagine we have an aggregate that is created, and its state is A, then it's updated, and it's updated, and it's updated. And now we get to a point where we say, well, let's assume the threshold for creating a snapshot is 4 events, right? This is not a practical number. In practice, it's more in the hundreds, but that reads a bit annoying on this slide. So let's assume 4 is a snapshot. What we can do is trigger a snapshot when we know we need to read 4 events from the event store to create the aggregate state. And what we do is we keep a little data store on the side in which we store the state that the aggregate had after applying event number 3. And we can add some more events. Now, when we load an aggregate, first we go check the latest snapshot for that aggregate. We check the sequence of the snapshot, and then load all the events that came after that snapshot to calculate the current state. Right. So in this case, we load the snapshot event, we load event number 4, 5, and 6. Oh, that's 4 again. So we need to create another snapshot. Now, the advantage of this snapshotting process like this is that you can do it asynchronously, right? You can just calculate snapshots at whatever pace you like. As long as the aggregate is cached, it will not require any loading anyway. We can still predict the number of events that we would need to load to reconstruct the aggregate. And then whenever we feel like creating a snapshot, that's when we add it, et cetera, et cetera. And what this causes is the cache invalidation spikes that we have are now reduced to maximum 5 events. Maybe rarely 6 because of this asynchronous processing, but now the spikes are down. And you can bring them down to whatever level is acceptable to you. Yeah. Yesterday I spoke to somebody who set the level to 1. Right? They said, we make a snapshot asynchronously all the time of an aggregate because we want the cache invalidation spike to be just 1. Right? So that's an option. So if you look at the command and projection sides, I've been talking only about the left side of things, right? There's snapshotting, there's consistent hashing, and caching that you can use. Preferably in that order as well. Don't start with caching and then the other ones. Apply them in this order, and you'll be fine for a while. Now there's the projection side. And that brings another nice challenge. So one of the promises that event sourcing gives you is you store all of history, or whatever part is interesting for you. For a specific component, you would store all of history. That means that you can do a replay, and you can get whatever new projection that you think of, you can base it on the beginning of time. So an event handler would basically normally tail from the event store, right? Whatever event is added to it, it will read and consume that event. But you can instruct an event handler to reset to the beginning. Or when you deploy a new one, it will by default start from the beginning. And that's great. It will just go all the way to the left and start reading those events, trying to catch up with the current events being added as fast as it can. Now there's a bit of a problem there. So a lot of clients, they use this and they like it and they use replays every now and then. And that's great. On an empty database, this is really fast. On a database with a few thousand events, it's also pretty fast. But as time moves on, it goes up. There's this graph again. And why is that? That's because the typical event handler that people write, and this is very convenient because it's easy and everybody understands it, it's just when an event comes in, you basically do three things. You fetch the current state of an entity with JPA, because that's easy. You update the state, that's also easy, just call a setter. And you persist the results. Now the persisting is very often implicit, but it still happens, right? That's great. Now, a typical order of magnitude of events, and this is what we had in our benchmark with the specific hardware that we used at the time. It was on a virtual machine with, let me get it right, 8 virtual cores. 8 or 4, sorry, can't remember exactly. But anyway, the replay, in that case, I mean, 250 per second could be a lot or could be not a lot at all, depending on what kind of environment you're in. But that means the typical workload of 10 million events takes 11 hours. That's pretty annoying. People do not like waiting for 11 hours to get a replay done. And the reason is event processing incurs some overhead, right? The framework also needs to do some stuff. There's other stuff than just the event handling that you see there. There's the starting of a transaction. There's ensuring that these tokens are loaded so you know for sure that that is the next event you need to be processing. Then there's the deserialization of events, right? They come from a network, so you need to spend time deserializing that. Then there's the actual event handler that is loading the model, making changes, and then updating the SQL. So there's a bit of overhead there. Now there's one thing, and in Axon that's pretty easy that you can do, is increase the batch size. Just don't do a transaction for every single event, but instead start a transaction, load a bunch of events, process them, commit the transaction, and move on. So we did a number of benchmarks. What's the best batch size for this specific application, right? So these numbers are not valid for whatever you're working on unless you're working on a really stupid card system that does nothing. So in our case, we saw that the best option for us was around 1,000 events in a batch, right? So we get about 4,000 messages per second just by setting the batch size to 1,000. That's the only thing we've changed, right? So that's a pretty good win. And in that case, replaying those 10 million events only takes 42 minutes, right? That's nice. If you have 1 billion events, and some of our clients have several billion events, well, it's still a couple of days, right? That is generally not acceptable. Especially not if you produce more than 4,000 events per second, because you'll never catch up. So it's not really the solution, but it's a partial solution. Fortunately, there's a lot more we can do. The other thing we can do is parallel processing, right? So this batch was a single-threaded event processor. Now we can process these events in parallel. And there's one specific caveat here, is that the event store that we have knows of global sequence, right? So all the events have this exact sequence. Now for us, parallel processing means there's a certain number of threads that can process events, and it does not matter whether these threads are in the same JVM or running on different JVMs. We do not allow communication between the threads for some coordination of work, right? Unfortunately, that means that generally they would need to read all events and discard the ones that are not for them. Right? There's a couple of optimizations, but let's say conceptually that's the way it works. So that means you'll get an increase when you add more nodes or more threads. And now I'm pretty sure it was a 4-core, 4 virtual CPU machine. You get some optimization, but it will stop at some point, right? There's, at a certain point, you will not have any benefit. In fact, it will just go worse. So 8 was the highest value we had here. So that's nice. So we can have 8 threads in parallel, process our events, and then let's see what happens. So, well, you can see what happens. We go up to 15,000. So we went to 250 to 4,000, and now we're at 15,000. That's a pretty big difference just by changing a properties file or a YAML file or whatever you prefer. So right now, our 10 million events are processed in 11 minutes. That's pretty nice. 1 billion events still takes 18 hours. That still does not fit in a day. It starts to fit in it fits in a around-the-clock day, but not in a work day, right? Nobody likes to work 24 hours. So we can do these batching quite fast now. But there's still something else we can do. Now remember, we have this naive solution of loading the current state and updating it and saving it back. What if we can make that logic slightly better? So we can optimize and make real good use of the batching that we're doing. And essentially, it means, first of all, we need to write whatever kind of statements that we use. So this example used a relational database. We also ran the benchmarks on Mongo, and we had very similar performance characteristics. But we can write these statements directly, right? Save us from loading an entity or loading anything from the database. So that should double it, right? Now in Axon, there's this concept called unit of work. And a unit of work is a place that coordinates all the activities that need to be done to process messages, right? And that unit of work also allows us to attach metadata. We call them resources. So they are basically batch-related resources, and we can attach this object that keeps a list of all the operations that we need to do against our database for that batch to complete, right? And that means that if we have several statements for the same entity, we can merge those statements into one. So let's imagine we have an insert operation for a certain order and a certain product, and somebody ordered 10 of these products, right? And it's a new order that an order that we never saw before. Oh, this is where I messed up. So assume an items added to cart event comes in for 10 products. Well, what we do is, well, that's an update, but instead of sending an insert and an update after, we just update the insert before we send the insert. So we go, oh, it's an insert of 20 now. Great, right? Now this is a fairly simple example, right? Just adding to a certain number. In practice, these operations are a bit more elaborate. And in that case, you really have to do the modeling that you would do on the data. You would spend that modeling time as well on what that update calculation would look like, right? So there's a bit of time and effort going into properly optimizing this, but it may very well be worth it, and that's really up to you to decide. So imagine we have an update operation and we add items added to carts, and well, that's great, we can do that as well. We can combine an update with another update. That's easy. But it gets really nice if we have an insert operation and then a remove operation arrives. We could just get rid of the entire operation at all. And especially in cases where you have a big likelihood of some entity not surviving the entire batch, right? Short-lived entities, this could be a good performance improvement. This executes very fast, I assure you. So here's a bit of, I would say, semi-pseudocode. It compiles, but This is conceptually how you would do it with Axon. It's you take the unit of work, you get a computer resource, and you tell that unit of work, if I created that resource, then on the prepare commit phase, so before you actually commit, I want to execute whatever batch operations that I've staged there. So this does not generate, or this is not beautiful code, right? And I'm not even referring to this, it's more of the batch operations, right? We're not, the readability of the code that you get here is significantly less than the code we have with the naive approach, where you just load an entity, update its state, and save it back, right? But there's a balance, right? There's some choices we need to make in what kind of optimizations do we need to do. So we ran this benchmark and we got to 30,000 events per second. So as expected, more or less, we doubled the throughput for these events. So now replaying takes us back from a couple of hours for 10 million events back to 5.5 minutes. Right. So let's look at the naive approach with 250 events per second. Took us 11 hours to process 10 million events, whereas now we're down to 5.5 minutes. If you consider the amount of effort you have to put into this, that is easy. That's easy win, right? And this is the kind of optimizations that you can do to make replays a lot faster. But there's an issue. The problem was not replay duration is not fast enough. The problem is the replay duration increases as we increase the amount of data. If I go back a bit, you can see it still increases, right? 1K events is still less than 1 billion events, of course, right? So this is still the problem. We go a lot faster, but we still go slower over time. We're just postponing the problem, right? That's fine if you're really close to your pension, otherwise, or when you're changing jobs, but otherwise it's still your problem. So there's this idea that, well, you don't always need to replay everything, right? It's not always necessary to go all the way to the beginning of time, right? In many cases, for a specific event handler or a specific replay or a specific view model, you can define a reasonable time frame. And in some cases, reasonable is 1 hour back. In some cases, reasonable is at least 10 years back. Typically, if you work for a tax authority, you have to go back 10 years. Now, if we have this reasonable time frame, we can reset the event handler to that specific time and start reading from there. Right? But now we have a challenge, because now we can get updates for entities or whatever updates we've gotten without the prior updates and without the creates, because they might have occurred in the unreasonable times of our application, right? So there's two ways to deal with that. So either be very lenient and just say, oh, it's an update for something we don't have, whatever, let's move on. Let's be flexible. Oh, we did an update and it updated 0 rows. Probably we don't care. Let's move on, right? That's the safest approach. That will give you all the entities of which the creation happened within our reasonable time frame. Now that may or may not be acceptable. A very common use case we see is, I want my view model to show all the applications that were active in the last year, right? So in that case, we have the creation of the application maybe before that year, but somebody did something the last year, so we need to worry about it. In that case, we can also do very selective ad hoc replays. We can say, oh, we missed the events of this specific entity. Give me the events prior to this one quickly. Right? Of course, in that case, it will be slightly slower, but at least it will not increase over time anymore. Right? We can now set a stable maximum of how long a replay will take if we have this reasonable time frame. This option is very often overlooked. We have some clients that they see this increasing problem and they They have this replay that takes 7.5 hours, and like, oh, we need to have this in a workday because we're not allowed to take anything down, or the process of upgrading should not take any longer than 8 hours, etc., etc. And this is a very nice solution. So going back to this architecture, or the architecture overview, so stuff that we can do that makes it very easy for us to improve performance, or parallel processing, batching. You can optimize your handlers, right? The event handlers, you can rewrite them to be much more efficient. And you have the ability to do a partial replay. You don't always need to replay from the beginning. So concluding, CQRS and event sourcing, they're at least interesting, right? Some people use it because it's interesting, it's different, and it gives them hope. But we have to take into account that they aren't faster, right? Using CQRS, or whatever architectural pattern for that matter, will not make you faster. It's not this magic pixie dust that if we go this way, it just moves faster, right? They're fast and they use CQRS. So if we use CQRS, we'll go fast as well, right? If that's the mindset in which you apply CQRS, you'll end up with the car I showed you earlier, right? So they're not the magic pixie dust, but what they do is when you give them the proper tuning, when you get these knobs and sliders and everything, there's all these little configuration options that you get. There's a lot of options, and they allow for much more focused and efficient, in my opinion, kind of optimization. Right? Separating these concerns of reading and writing allows you to focus on much smaller areas where you can really dedicate your effort into optimizing that one part where you need it, whereas the rest, don't care about it. If it runs fast enough, stop caring, move on to something that's more important. So if you want some references, some information, more information about the stuff that we've been building. Axon Framework is completely on GitHub. It's an open source Apache 2 licensed framework. So play around with it. There's a getting started guide. There's lots of easy Spring Boot tutorials as well. Yeah, there's a quick start on axonic.io/download. You should be able to get up and running within 5 minutes. And if you don't, that's how you can contact us to complain. So with that, I would like to thank you, and I wanted to leave some time for questions, and I guess I managed. So, thank you.
Thank you, Allard. Thank you for your talk. As far as I understand, you said that the more preferable storage system is NoSQL for SQRS, yes?
Actually, no. So the best storage you can use is a dedicated event store, right? Which you could consider a NoSQL type of store.
Okay, let's assume that we have NoSQL, yeah? Can we go back to slide when we are the common event handling you have in your presentation slide, yeah? When it's 3 or 4 steps to process.
No.
For the first one, you are getting some information.
You're loading, you're changing.
Yeah. So yeah, this one. So my question is, what about the fact that you don't have transactions in NoSQL? So you are fetching something at first hand, and then you're updating state. So you're saving this event, and then you're calculating something and saving. So between 2 saves can be anything. So yeah, this one.
It depends. That's your global answer. No, I will tell you what it depends on. I'm not the it depends and then walk away kind of person. The thing you can do is you can at least in Axon you can define the your ordering expectations of events. So you can specify, I want my events that speak about, in this case, the same card. I want to get them in the order they were stored in the event store. In that case, there will never be concurrent updates on the same card, because all the updates of the card are sequential and they're given to the same thread for processing. Right. So this is the component that updates that specific table. Then that table will, or entities there, in what I said table is whatever collection, if you're using Mongo, they will be updated sequentially. So there are ways to guarantee that this component is the only one updating and there's no concurrent updates at all. So even without transactions, you are safe when it comes to this. You are not entirely safe when it comes to doing an update and storing a token, which records the progress. In that case, you need to choose whether you want to risk duplicate processing or skipping a processing. At least once, at most once. You pick one. With a full transactional data store, you actually get exactly once processing. Mm-hmm. So you do at least once delivery, but then to make sure that the transaction, if it failed, you'll redeliver automatically.
Okay, thank you.
Right. Thank you for a great talk. A question a bit aside. I'm here.
Where's there you go.
Here, yeah. So about events log, should we care about events log size? I mean, it keeps growing during the time, yeah, and new events coming and saved into database. It's just growing in the size. So should we maybe clean up it from time to time, or is it just a matter of a new RDS node or so? Just extending database. What is your opinion?
Yeah, so deleting data is always a topic that comes up after a couple of years, right? Should you care? Well, yes, probably. If you have an indefinite amount of money, anyone? No? Then you don't have that problem. You just buy disks. You just say, hey, Google, you got some? Oh, Amazon, you got some? Okay, that's fine. But we don't have that. So yes, you do need to care, but you always need to balance the value of the events that you have versus the cost that you have, right? Now, value of very old events is likely to be slightly lower, right? But you can also put the cost of storage slightly lower because you can store those events on cheaper storage, right? So typically what you see is the most recent events, you keep them on SSDs in very, very close to your event store, very close to your applications. Whereas as events grow older, you can store them in the regional data store on slower, cheaper disk because you don't need to access them as fast. And in general, a spinning disk, or not in general, in some cases, spinning disk is faster at reading sequentially than an SSD is. SSD is really good at reading from different places at the same time. So there's some balances, and then the cheapest storage is dev null, and that's where you can eventually write your events to if they really don't represent enough value anymore to store at all. Yeah. Which in case of auditing, well, auditing is always lots of value, so in that case you don't. But as soon as the auditing time is over, you might want to just throw them away. Yeah.
Thank you for the speech. I've got two questions. First one, probably obvious. What are the benefits for Axon comparing to Kafka streams?
Yeah, there's a lot of debate on that. So I'm not an absolute Kafka expert. So I'm doing a bit of hearsay here, okay? So, but bear with me. There's a lot of discussion on whether Kafka is suitable for event sourcing, right? Where the big difference was getting events from A to B. Kafka can do that very well, right? No problem at all. Getting it back to A and ensuring the consistency when you insert, that's where Kafka has some problems. It cannot give this consistent check on consistency check on the sequence of events, so that's mainly the big functional difference. And conceptually, Kafka was designed, or initially Kafka was designed to store events or store messages for a certain limited period of time, where that period of time could be so large that it's practically unlimited. But there's some that argue that, well, that Kafka is not designed for that and it will incur some performance costs if you do. I'm not sure if that's true, but and whereas the event store was designed to store forever unless you wanted less than that. So it has slightly different design aspects to it. That's what I know, what I can tell you about it. Yeah.
Thank you for the answer. And the other one would be more like a throwing stuff at the fan. You're probably familiar with Martin Fowler. And this is just a quote from his CQRS wiki. While I have come across successful uses of CQRS, so far the majority of cases I've run into have not been so good, with CQRS seen as the significant force of getting a software system into serious difficulties. How you would comment that?
Does it mention the time in which he said that?
Just a second. Oh yeah, actually this one is pretty old one. It's 2011, but I heard this quote more fresher time, 2014,
yeah,
15.
because people repeat quotes. So it might be a coincidence, but at that time, Axon was not very well known. Okay, just saying. But you know, to get to the real answer, so it's actually one of the biggest and very successful projects that I know of was run by ThoughtWorks with Axon and CQRS. The problem with CQRS, as with any new kind of not so much technology, but design principle, we have to get used to that, right? There's, especially in 2011, CQRS was very new. So we did not know what kind of trouble we would get into. And I would definitely, very strongly recommend reading up to DDD and practicing that, because that is your lifeline into CQRS. You get your DDD wrong, you'll get your CQRS wrong. If something feels uncomfortable in CQRS, don't push it, don't go on. You're making a mistake, right? The uncomfortable feeling, that is your design telling you you've made a mistake. Don't ignore it, right? That would be my advice in some quotes in 2019 that you might use.
Thank you for your talk. I have several questions. One of them is what you should do if event reordering occurs.
How do you mean event reordering?
For example, if we push several events and in network we have a reordering. For example, we push them in the sequence 1, 2, 3, and we get in the framework in the sequence 2, 3, 1 event.
Yeah, so that's not going to happen, and I'll tell you why. This comes back to do your DDD right. So one aspect of domain-driven design is get your aggregate boundaries right. Your aggregate boundary is a consistency boundary. Whatever happens in that consistency boundary is all, let's say, is all sequential in the end, right? There's a very clear definition of what happened before what other thing, right? In that case, when you send events, they have a sequence number already, so we know in what order they need to be stored. However, events from different aggregates can still overtake each other, right? In that case, they could have happened in 1, 2, 3, and they get stored 1, 2, 3. But because we've designed the aggregates the way we designed them, we don't care. They are fine. There's no guaranteed absolute ordering in that case. So they just get inserted whenever they are. So in our case, it's the commit, the time where you send the commit, or the commit arrives in the event store. That's where the order is defined, right? So the first commit that gets a block of data, and while it's writing the events in that block, the second commit can get the next block and start writing there as well. So you can have concurrent commits, but they are ordered in the order in which the commits arrive. So yes, it is possible that, you know, because of concurrency, events happen, but that should not matter because of the way the aggregates were designed. And these are unrelated updates.
So you mean that it's a design problem?
Yes.
Okay.
I think we had, if we have time, there's one more question there.
No, so
No. Maybe I'll see you in the discussion zone afterwards.